A quark star is a hypothetical type of compact exotic star composed of quark matter. These are ultra-dense phases of degenerate matter theorized to form inside particularly massive neutron stars. The existence of quark stars has not been confirmed theoretically or astronomically. The equation of state of quark matter is uncertain, as is the transition point between neutron-degenerate matter and quark matter. Theoretical uncertainties have precluded making predictions from first principles. Experimentally, the behavior of quark matter is currently being actively studied with particle colliders, although this can only produce hot quark-gluon plasma blobs the size of an atomic nucleus, which decay immediately after formation. There are no known artificial methods to produce or store cold quark matter as it would be found in quark stars. Creation. It is theorized that when the neutron-degenerate matter, which makes up neutron stars, is put under sufficient pressure from the star's own gravity or the initial supernova creating it, the individual neutrons break down into their constituent quarks, forming what is known as quark matter. This conversion might be confined to the neutron star's center or it might transform the entire star, depending on the physical circumstances. Such a star is known as a quark star. Stability and strange quark matter equals, ordinary quark matter consisting of up and down quarks has a very high Fermi energy compared to ordinary atomic matter and is only stable under extreme temperatures and/or pressures. This suggests that only quark stars comprising neutron stars with a quark matter core will be stable, while quark stars consisting entirely of ordinary quark matter will be highly unstable and dissolve spontaneously. It has been shown that the high Fermi energy making ordinary quark matter unstable at low temperatures and pressures can be lowered substantially by the transformation of a sufficient number of U and D quarks into strange quarks, as strange quarks are, relatively speaking, a very heavy type of quark particle. This kind of quark matter is known specifically as strange quark matter and it is speculated and subject to current scientific investigation whether it might in fact be stable under the conditions of interstellar space. If this is the case, quark stars made entirely of quark matter would be stable if they quickly transform into strange quark matter. Strange stars equals, quark stars made of strange quark matter are known as strange stars, and they form a subgroup under the quark star category. Strange stars might exist without regard of the Bodmer-Witten assumption of stability at near zero temperatures and pressures, as strange quark matter might form and remain stable at the core of neutron stars, in the same way as ordinary quark matter could. Such strange stars will naturally have a crust layer of neutron star material. The depth of the crust layer will depend on the physical conditions and circumstances of the entire star and on the properties of strange quark matter in general. Stars partially made up of quark matter are also referred to as hybrid stars. Theoretical investigations have revealed that quark stars might not only be produced from neutron stars and powerful supernovas, but they could also be created in the early cosmic phase separations following the Big Bang. If these primordial quark stars transform into strange quark matter before the external temperature and pressure conditions of the early universe makes them unstable, they might turn out stable, if the Bodmer-Witten assumption holds true. Such primordial strange stars could survive to this day. Characteristics: if the conversion of neutron-degenerate matter to quark matter is total, a quark star can to some extent be imagined as a single gigantic hadron. But this hadron will be bound by gravity, rather than the strong force that binds ordinary hadrons. Strange stars equals, recent theoretical research has found mechanisms by which quark stars with strange quark nuggets may decrease the object's electric fields and densities from previous theoretical expectations, causing such stars to appear very much like nearly indistinguishable from ordinary neutron stars. This suggests that many, or even all, known neutron stars might in fact be strange stars. However, the investigating team of Prashanth Jayakumar, Sanjay Reddy, and Andrew W. Steiner made some fundamental assumptions that led to uncertainties in their results large enough that the case is not finally settled. More research, both observational and theoretical, remains to be done on strange stars in the future. Other theoretical work contends that a sharp interface between quark matter and the vacuum would have very different properties from the surface of a neutron star. and, addressing key parameters like surface tension and electrical forces that were neglected in the original study, the results show that as long as the surface tension is below a low critical value, the large strangelets are indeed unstable to fragmentation, and strange stars naturally come with complex strangelet crusts, analogous to those of neutron stars. Other theorized quark formations, Jaffe 1977, suggested a 4-quark state with strangeness. Jaffe 1977 suggested the H-di baryon, a 6-quark state with equal numbers of up, down, and strange quarks. Bound multi-quark systems with heavy quarks. In 1987, a pentaquark state was first proposed with a charm anti-quark. Pentaquark state with an anti-strange quark and 4 light quarks consisting of up and down quarks only. Light pentaquarks are grouped within an antied couplet, the lightest candidate, O+. This can also be described by the diquark model of Jaffe and Wilcock. O++ and antiparticle OVA. Doubly strange pentaquark, member of the light pentaquark antied couplet. Charmed pentaquark OC, 3100. State was detected by the H1 collaboration. Tetraquark particles might form inside neutron stars and under other extreme conditions. In 2008, 2013 and 2014 the tetraquark particle of Z, 4430, was discovered and investigated in laboratories on Earth. Observed over dense neutron stars, statistically, the probability of a neutron star being a quark star is low, so in the Milky Way there would only be a small population of quark stars. If it is correct, however, that overdense neutron stars can turn into quark stars, that makes the possible number of quark stars higher than was originally thought, as we would be looking for the wrong type of star. Quark stars and strange stars are entirely hypothetical as of 2011, but observations released by the Chandra X-ray Observatory on April 10, 2002 detected 2 candidates, designated RxJ 1856.5-3754 and 3C58, which had previously been thought to be neutron stars. Based on the known laws of physics, the former appeared much smaller and the latter much colder than it should be, suggesting that they are composed of material denser than neutron-degenerate matter. However, these observations are met with skepticism by researchers who say the results were not conclusive. And since the late 2000s, the possibility that RxJ 1856 is a quark star has been excluded. Another star, XTEJ 1739-285, has been observed by a team led by Philip Carrett of the University of Iowa and reported as a possible candidate. In 2006, YLUAL, from Peking University, suggested that PSABO 943 plus 10 may in fact be a low-mass quark star. It was reported in 2008 that observations of supernovae SN 2006 GY, SN 2005 GJ and SN 2005 AP also suggest the existence of quark stars. It has been suggested that the collapsed core of supernova SN 1987A may be a quark star. See also: quark nova, quantum chromodynamics, neutron stars, a Euroneutron matter, a Euroneutron degenerate matter, a Euroneutron, deconfinement, Tolmani Oppenheimer, a Volkoff limit on the mass of a neutron star. Compact star, exotic star, neutron star, pulsar, manta, white dwarf, stellar black hole. Degenerate matter, QCD matter, quark, a quark-gluon plasma, strangelet, quark matter, neutronium, prion matter. References: Quark star on arXiv.org. External links: Jaffe, are perhaps a stable dihyperon. Physical Review Letters 38, 195 198. Bibcode, 1977 PHRVL 38195J doi, 10.1103/Phys Rev Let 38.195. Neutron star quark star interior, quark star glimmers, Nature, April 11, 2002. Debate sparked on quark stars, CERN Courier 42, No. 5. Wish upon a quark star, Paul Beck, Popular Science, June 2002. Drake, Marshall, Driesler, Freeman, Fruscian, Judah. Cashiap. Nicastro. Al is XJ185635-375 a quark star? Astrophysical Journal 572, 996 a 1001. AR Ziv, Astro PH/02041159. Bibcode, 2002 APJ. 572-996 DDoy, 10.1086/340368. Perhaps a 1,700-year-old quark star in SNRMSH 15 to 52, curious about astronomy, what process would bring about a quark star? RxJ185635-375, candidate quark star, astronomy picture of the day, April 14, 2002. Quarks or quirky neutron stars. Mark K. Anderson, Wired News, April 19, 2002. Strange quark stars, ask an astrophysicist, question submitted April 12, 2002. Seeing Strange Stars, Phys.org.com, February 8, 2006. Quark stars could produce biggest bang, spacedaily.com, June 7, 2006. Meissner effect in strange quark stars, Brian Niebergel, webpage, University of Calgary. Irina Saget. Merjam Y. Tosca. Jurgen Schaffner B. Leitch. Strange exotic states in compact stars. Journal of Physics G32, S241 a S249. AR Ziv, Astro PH/0608317. Bibcode, 2006 JPHG. 32 S241 SDOI, 10.108832 Quark stars involved in new theory of brightest supernovae. The first ever evidence of a neutron star collapsing into a quark star is announced, Space.com, June 3, 2008. Quark stars, alternate view column Avenue 114, John G. Cramer, published in the November 2002 issue of Analog Science Fiction and Fact magazine.